our Veolia Water Tech Talk today. I can see that we've got a few people that are still in the process of logging on. So we're going to give it about another 30 seconds or minute or so, and then we will get started. So thank you for your patience, and we'll get started shortly. Okay, I'd like to welcome everybody to today's webinar. My name is Jill Browning, and I'll be your moderator today for our webinar on Optimize Your Wastewater Facility with AI to Maximize Treatment Capacity and Delay Costly Expansions. Before we get into our presentation today, I do have just a couple quick housekeeping slides to go over. First of all, hopefully you should be able to hear me speak right now. But I do want to mention that should you have any audio difficulties throughout the presentation today, that there are two different options to connect to your audio. So feel free to switch back and forth between those should you have any issues. So you can use your computer or call in via your phone. And then also I do want to mention that due to the large number of attendees that we do have on today's presentation, we have gone ahead and muted everyone's lines. But no worries on that. We do want to still make this as interactive as possible. And in terms of interacting with today's presenters, you can ask your questions via the questions panel anytime throughout today's webinar. And then at the end of today's presentation, we do have some time set aside for a Q&A session with our speakers. So feel free to ask any questions that come to mind, and we'll try to get to as many of those questions at the end of the presentation as time allows. Today's webinar is one of many in our upcoming Veolia Water Tech Talks program. And specifically within the month of May, we are featuring digital transformation. So today's webinar, along with two additional ones on May 11th and May 25th in the realm of the digital transformation. So feel free to check those out over at www.veoliawatertech.com, as well as the remaining or the rest of the Veolia Water Tech Talk series program. And then additionally, we have made available our collection of on-demand webinars that we've conducted over the last few years. And you can go ahead and access more than 40 on-demand webinars over again at that www.veoliawatertech.com site. So feel free to go over to the website, browse the various topics, and then register for any of those that you may see of interest for you as well. One other housekeeping note is a PDF participation certificate will be made available to you at the conclusion of the webinar. You should receive that within approximately 1 to 2 days after the webinar. And then also at the end of today's webinar, you'll receive a quick survey requesting your feedback. Should take no more than 20-30 seconds or so of your time. And for those of you who do complete that survey, you'll be entered into a drawing to win, or a chance to win, a $25 Amazon gift card. So if you would be so kind to fill that out for us, we do greatly appreciate all of your feedback. Now, before we hop into the main part of our presentation today, if you're not familiar with Veolia Water Technologies, we are a leading water and wastewater technology provider, and we offer our clients a variety of technologies, services, and projects. So you can learn a little bit more about us over at that website, or feel free to contact us at the conclusion of the webinar today as well to learn a little bit more about our capabilities. And then also we support our clients through a variety of different markets, some of the industrial markets that you can see over on the right side, as well as the municipal market, to help support those water and wastewater treatment needs. So with that, now I would like to introduce our speakers for today's presentation. Martin Casper is Director of Digital Transformation for Veolia Water Technologies. During his time at Veolia, Martin has successfully led engineering, project management, and sales teams, and he is currently responsible for the aftermarket and services department, which includes the deployment of Hubgrade, Veolia's digital offer. And our second speaker that we have with us today as well is Louis Larson. Louis is a digital business development engineer for Veolia Water Technologies, and he focuses on accompanying clients in digitalization and using data as a lever for operational excellence and minimizing environmental footprint. So with that, I will like to turn it over to our speakers today, and I believe we've got Martin with us first.
Yes, well, thank you, Jill, and thank you all attending today. Basically, before we start, we just want to start with a simple question. I mean, why are we doing this? Why are AI and digital twin in wastewater treatment? And what outcomes can we generate from those new tools? Well, a simple answer to that is basically because we have to change. We're facing the climatic crisis. Water is directly impacted by climate change, whether through its quality, availability, but water also is a very strong vector of climate change to ecosystems and population. So in order to understand better the behavior of climate change and the impacts of it, I mean, we all know that we need more data. But data for us cannot do the work alone. I mean, we're not doing digital for digital. We have to do it on a specific purpose, with a specific purpose. And our mission, and as water experts, is basically to preserve resource and help population to go through that transition. So we can talk about Industry 4.0, we can talk about IoT, but we must remain very vigilant to keep human at the center of our work, basically. And to do that, we can start with a very simple example. We can talk about a wastewater treatment plant located near the sea, very nice, and we've got some nice windmills getting energy from the wind. So we know that aeration typically takes most of the energy or the biggest portion of the energy draw from a wastewater treatment plant. But when you look at those two items, energy consumption at a wastewater treatment plant and windmills, for example, producing energy only when wind is active, they seem kind of a bit disconnected together. So we had discussion with the plant operators and the plant experts, and together we thought about another way of doing things. So is there a way we can take more data, other sets of data that typically are not looked at by plant experts, and find a new dynamic model which could take energy from the windmills when the wind is there, and after that give back energy to grid, or take energy from grid when the prices are low. So this new approach, those new opportunities that are generated by powering data and at the same using the human expertise is really what we think will help us to go through a smooth transition. So if you dig a bit more in our subject, basically, we can think about we have already deployed our platform and our tool to over 100 wastewater treatment plants, but we cannot provide a custom solution or a solution that will fit everything. So we have to focus and deliver value when there is specific case. So for us, the sweet spot of what we bring, of the value we bring, is basically when you have a plant that is medium size, typically with a high hydraulic load or biologic load, and we need to do an expansion, for example. So instead of building those huge concrete tanks and those massive expansions, looking at data available, looking at other sets of data, sometimes can give us a new road to think differently. And when we talk about one of the savings we see are obviously chemicals and also in energy cost. And when we talk about energy cost, when we look at real industrial price that are paid in Europe, for example, we see that there's much more similarities between the price that are paid in North America versus the price that is paid in Europe when we talk industrial electricity rate, which is completely different with the household electricity rate. And when we talk about a cloud solution, we cannot escape the cybersecurity aspect. By nature, cybersecurity is not a very attractive subject, but with more connected objects, it is something that must be native. It must be there at the start, and it must be done in the best possible way, meaning working with third-party suppliers that are certified, that are trustable, and that the processes are used already and deployed on other sectors. Could be on drinking water networks, could be on the banking side, could be on the aeronautic side as well. So let's start with, let's just go a bit deeper now in our subject, and Louis will give you some very applicated example. But a lot of question when we start talking about AIs suddenly turn to automation guys. And I think that's really important to know that the outcomes generated by smart controls or real-time controls are not for automation guys. The outcomes generated from a smart approach are really on the process side. All wastewater treatment plants are typically delivered with tailor-made code, typically ladder logic, with simple local decision. Could be yes or no, A or B, and you look at the fixed sets of data, which is basically reviewed by the PLC. So PLC are typically very robust, but are limited in the sense that they cannot optimize, they cannot think differently, they cannot look at other sets of data and change the way they behave, basically. And this is where the smart approach comes in. So the smart approach will basically be able to look at weather forecast, electricity price, human behavior around the wastewater treatment plant, and will, with the process team experts at the plant, will recommend to change the PLC set points to be able to capture the value that is hidden today from the PLCs. And this is really for us the main interest of bringing this AI into the wastewater field, and this is the value we've seen. So I would like to turn it to Louis. Louis is an expert on that, and he will show you some real specific case that where we have had very good success of applying our digital platform.
Thanks, Martin. Great intro. I'll try and pick it up from here. So Martin introduced the concept of real-time control, optimization, and using AI. This can always feel a bit cryptic or a bit distant. I will, as well as possible, try and make it real down on the wastewater treatment asset. So the first thing I wanted to show here is, what does a typical control or adaptation of the operation in a wastewater treatment plant look like? So you have the time of the day on the x-axis, and then you have any kind of load and control on the y-axis. So the load that is changing is the blue line, and the red one could be your energy consumption or your chemicals consumption, or the kind of set points that your PLC would issue to handle the incoming load. And on a typical setup, you would have something that looks like the red line. So a bit in ladders, it's load adapted, it's optimized, it's above the needs of treatment from the blue line, which is the load. And that's thanks to the local expert of the operator that knows his plant, the PLC that was programmed, the equipments and sensors that you have installed there. So it's very secure, it's robust, and it's giving a good and compliant result. But it's not optimized 100%. If you had a system that could rerun all the possible scenarios at all times through equations and knowledge and data that comes from outside the fence from the asset, you could do something that's a bit more tailored to the need. And this could look something like this. So where your red line is really following your load all day long and optimizing your energy consumption, your chemicals consumption, how you're using your existing physical asset in the best possible way. So you have optimization algorithms that would run on all the data that is available both on the site and outside the site. It could compare best practices from similar plants. It can use predictive modeling to forecast what the incoming load is going to be based on data series coming from anywhere or similar plants. It can use energy prices, as Martin told, or even weather data from a local radar station. And here at Veolia, we've also chosen to embed it with the knowledge that we have of operation of many plants from across the world. So you can pull all these know-hows together and get something like this, where ultimately you're still remaining compliant all the time and you're following exactly your needs. You're just doing it in an optimized way, thanks to this huge volume of intellectual capacity that AI and cloud and Industry 4.0 ultimately gives you. So let's try and dig even further down on what would it look like in a typical day-to-day scenario on your wastewater treatment plant. So I've tried to draw up a little very simplified wastewater treatment plant here. You have your flow on the left, which is your wastewater that comes in. It goes through a couple of process steps, and then it gets to the biological treatment part, where you have a denitrification zone and a nitrification zone. Of course, here it's in the case where you have probably total nitrogen requirements. But this is, of course, just an example. So you'd have your load, it comes into denitrification, and then the nitrification goes through the clarifier, where the SS is sorted, and you've got your clean run water that runs out to the effluent, and you keep the fishes safe. But what happens if suddenly it starts raining heavily? Your flow is going to change, it's going to rise, and it might put your plant at a risk of a sludge escape, or even making you non-compliant. So the way that you could use real-time control to optimize this is to look at your existing process steps in a different way and use them in a dynamic way. So maybe the flow would enter and would immediately be treated by nitrification and then denitrification in alternating phases based on the concentration you have of nutrients in this. In the beginning, you might have a lot of nutrients from a drier period, but then it becomes rainwater, so there's less treatment needs on this. So maybe treatment in one tank would be sufficient. And you then use the second tank that originally was nitrification as an extra clarifier. So you recirculate some of the sludge that you had in your clarifier, and you let it settle at the bottom of your nitrification tank, as you see in the second one with the little S here. In this way, you will give the plants extra settling capability, and you will reduce the sludge blanket in your existing clarifier, thereby giving it higher hydraulic capacity where more water can flow through and still protect your recipient, without having to build extra capacity to handle this increase in load. And this, of course, is only a temporary thing. So you only do it whenever the flow is above a certain limit in need of treating a stormwater event. To build upon the hydraulic capacity of a wastewater treatment system, you can look inside the fence like we just did for the plant. You can also look outside. so your sewer system. Both are inherently linked. The water will flow from your sewer system to your wastewater treatment plant. So say we take the same example as before, without real-time control, you will have rain somewhere in your system that will fall into a tank, a basin, or a pipe, and by gravity will flow downstream all the way down to the plant. But water doesn't always fall evenly, and it just flows wherever it can. So suddenly that's why you have the example here where you have 20% and then 40% and then 100%. You might be in a place where you have enough volume, but there's just too much in one place at one time, which causes a runoff or a CSO. You can see that on the red line, which ultimately leaves untreated water directly out to the receiving waters. The additional non-controlled flow that you're getting also to your plant can put your plant at risk of a sludge escape, as mentioned earlier. But isn't there a way where we could use the additional 80 and 60% from the two other tanks to maybe help out this whole system and avoid all this? You probably guessed it, but real-time control could be the tool to do that. Thanks to algorithms that would know where and when the water would fall from weather forecasts and from controlling the pumps and the basins in your sewer system. You may be able to retain some of the water in some places, distribute it according to the volumes available and the forecasts you have. In this way, you can make sure that you don't have any CSOs without building extra volumes, and at the same time, you can even out the flow nice and easy down to the wastewater treatment plant and secure the sludge blanket and thus minimize the risk of a sludge escape. So by looking at it in a holistic way outside the fence, thanks to this Industry 4.0 approach, you can actually do much more with what you've already had. So I hope this was an okay introduction to the concept of using digital to make more of your asset. I will try and give just a little extra explanation on how we see a possibility to do that. So if we draw this graph with time and flow on the X and the Y axis, and that the purple line here illustrates the capacity, the hydraulic capacity that a wastewater treatment plant can handle in a normal situation without ATS. In this case, ATS stands for aeration tank settling. This is the concept that I explained earlier with the temporary additional clarifier within the biology. This type of process is called aeration tank settling, or ATS. So now we're drawing a flow here. So we can see that there's a normal flow in the beginning, and then at some point it probably starts raining and the flow rises. It rises so much so that it goes above the capacity of the plant. If you're able to introduce aeration tank settling, you're introducing a temporary clarifier. You're therefore raising your hydraulic capacity. That's why we now have a new purple line above the previous one. So if we were able to know when to start the process of aeration tank settling, because we would know when the water arrived to the wastewater treatment plant, we'd be able to raise it from one line to the other. So this could go for something like flow forecast, so incorporating weather APIs, radar forecast data, what have you, which is the more advanced solution. It could also just be a rain gauge from somewhere up in the system, which would be enough of a warning that we know the water is in the sewer system, which means it will eventually arrive at the wastewater treatment plant. So you can incorporate both data series, one or the other according to availability, and then maybe be able to react earlier. And if you don't have any kind of forecast, you can only start reacting when the water is at your gate, when it comes in. That's why we start raising, if you introduce it at that moment, you only start raising your capacity at the moment where the water kind of reaches your plant, which is the point where it goes above, probably above the hydraulic capacity. Say that you'd be able to push that diagonal red dotted line to the left, you would essentially be prepared and avoid the risk of washout that you have, which is the area in purple. With flow forecast, we move this one to the left because hours in advance, we know it's going to rain, there's going to be a lot of water coming in. Therefore, we can start pushing the sludge from the clarifier back to the biology, turning off the aeration, turning off the mixing, letting it settle nice and easy down there, and benefit from the additional sludge blanket in the existing clarifier. So I hope that that made it kind of clear of how we see that dynamically we can change the layout of a plant while using its existing infrastructure to make it handle better a specific situation, a couple of hours of rain event, for example, and then go back to normal operation afterwards once the flow goes back below the normal line. But it isn't always necessary to have, for example, additional hydraulic capacity. We can also look at biological capacity. So process intensification. I know that I need to meet more stringent effluent requirements, or I'm having trouble handling the extra load that is coming in from a nearby industrial site that has just been linked to the network. Could be a million reasons. Using the same logic as before of optimizing your existing volumes, if you have more data, for example, in this case, we've introduced nitrate and ammonium sensors in ammonium in both tanks and nitrate in one tank, we can start using the process volumes dynamically. So nitrifying and denitrifying whenever the level of the concentrations of nutrients require one or the other. And by always monitoring what is going to be in the biological tanks, we know that what is going to go further down to the clarifier will always be within the compliance and not doing over quality, not over aerating if ammonium is down towards zero. Then there's maybe a lot more value in starting a denitrification phase that would lower the nitrates, which would save you money and at the same time lower your overall TN concentration for the outlet. Another thing that could be done is also, if you look at the sludge blanket in a normal operation time where flow isn't going high, you can maybe push your sludge blanket a little higher in your clarifier, which gives you additional free hydrolysis from the sludge that's present in the clarifier. You're not at risk for any sludge escape because you always have the safety of knowing that I have my forecast, I know when the water is going to come, so I know when I need to start pumping the sludge out. And the system will react in real time because it is always checking all the data that is available. So that's how you can stretch your biological capacity. Previously, I mentioned mostly example regarding total nitrogen treatment, but more and more there's focus on phosphorus removal. And we've developed a patented series of algorithms to try and help those wastewater treatment plants that have not been built for this purpose, but that might end up in a situation where they need to start treating for it. One solution is, of course, to dose a lot of chemicals. From an environmental point of view, it's not great. From a cost point of view, it's not great either because chemicals can be very expensive. Especially when you think about the fact that there is inherently and naturally bacteria in your sludge that can help you boost and get you through this phosphorus removal process, which are your bio-P bacteria. So thanks to the real-time control, what you can essentially do is that you can try and look for times in your existing volumes where you want to introduce anaerobic situations that would promote the growth of your bio-P bacteria, which then later on will be able to absorb more and absorb more of the incoming nutrients, and thus limiting the amount of chemicals that you would have to dose by a significant amount. So here, what we've done is that the algorithms we've developed are adaptable to any kind of activated sludge plant. You've got 3 typical categories here at the bottom of your screen: biodinitro, biodinifo, your single ditch, 1 tank typical setup, or your recirculation plug flow plant. In all of these, the principle of how we do this is the same. We know that there is no anaerobic volume in the design, but by following the load and the flows throughout the day, we can probably, late at night, for example, find a slot where the concentrations and the flow is so low that by stretching the denitrification phase long enough, you get anaerobic conditions. And suddenly that's when the BioP bacteria start growing and are in their ideal state. So if we take the example of the recirculation plug flow plant here, by turning off the aeration dynamically by sending a set point to the PLC, we stop the recirculation of nitrates and move from an anoxic phase to an anaerobic phase. And that's when you get your growth of BioP, which translates into reduction of chemicals for precipitating it later. So this is the way we address additional biological capacity on an existing asset that wasn't built for the purpose of it, but suddenly you can start trying to meet your effluent requirements. This all sounds nice. There's a ton of drawings and nice concept, and theoretically, I hope it makes sense for all of you, but seeing is believing. So I wanted to show you some results that we've gotten with actual clients that we've worked with and who are benefiting from the use of these algorithms and real-time control right now. Many of these algorithms are running around the world, and some of them have been developed and are running here in Denmark at the moment. So the plant I'm taking you to is a bit south of Copenhagen, the capital, in the region of Køge. It's 100,000 PE in capacity, about 20,000 cubic meters per day, or 5 MGD. I hope that speaks to everyone. And this client was faced with 2 main issues. So first, they needed to reduce their operational costs. That's fairly regular, but they were out on the market to see if there was any way to save a buck here or there. Additionally, in Denmark, when it rains, it can really pour. So sometimes the guys were faced with sludge escapes when heavy rain events were coming in. And there was a quite manual way of handling this. So the guys would be called in the middle of the night on a phone, and they had to come in and try and kind of do whatever they could to keep the sludge within the existing volumes and still remain compliant. And it basically was a mess. They were spending a lot of time on it, and it wasn't always ideal, and it was very reactive, almost too late. By implementing a set of 9 different features or algorithms from a cloud digital platform and benefiting from real-time control, they actually achieved some quite amazing results. And just to say that this plant was actually quite well automated already. They had already a kind of real-time control to help them optimize aeration that had given them substantial operational cost savings. But they moved away from this one because it didn't have any aspect of handling hydraulic events. So instead, they switched over to the solution I just described and were able to start doing BioP removal, even though the plant was not designed for it, as shown before, and increase their hydraulic capacity in an automated way. So this translated to 3 things: an energy reduction of 25% of air or kilowatt hours to your aeration tanks. So the blowers were used significantly less after introduction of the real-time control. Furthermore, during rain events, they were able to handle 100% more flow through the biology. So there could be twice the amount of water that was usually going through without the risk of such escape here. This is, of course, not all the time, but within the time span of a stormwater event. And finally, they needed to abide by a specific phosphorus concentration at the outlet, which they were just dosing their way to at the moment. With the dynamic anaerobic volume idea that I introduced to you earlier, they were able to reduce by 60% their chemicals for precipitation. So this translated, of course, on top of the aeration saving to quite a significant cost saving for them. So this was one example. We'll move within the same country, but to another client, a bit of a smaller plant. Just to put some other numbers on, for example, the possibility to avoid or postpone an expensive CAPEX investment. So this plant was about 12,000 cubic meters per day, 3 MGDs or 60,000 PE. And they were just really focused on trying to increase their hydraulic capacity. There was a lot of water coming through, and they'd had a couple of events with sludge escapes that then made them non-compliant because of the lack of sludge in the plant, and yeah, it was no good. So here, with the same concept as described earlier with the aeration tank settling, so the last section of the aeration modified into a temporary settling tank, where the whole plant gets optimized by 5 different types of real-time control algorithms that always check what the data available at the plant is and when is the water coming, etc., etc. Actually managed to stretch the biological capacity by 70%. So we went from 1,200 cubic meters per hour of capacity before going into risk of washout to 2,000 cubic meters per hour. So that's a 70% increase, which is really significant. And now the operators didn't need to intervene on that because the system figured it out itself and told the PLC how to handle it. So when to turn on or off a pump or an aeration or start pumping more or less. And in this way, they avoided actually completely of having to build an extra clarifier, which was the original idea. So I thought this was a good example of how, with actually existing volumes, you probably will be able to do more with less, just thanks to a lot of data and a lot of numbers crunching. And I think that for this side, I'd like to pass it on back to my colleague Martin.
Yeah, so thank you, Louis, for those very relevant example. What we tried to do in this first webinar is basically to introduce you to the tools we've developed. And in the context of the climate change, pressure on resource will only increase. So we have to basically use all possible tools available for us to obviously preserve the most precious resource, which is water, but also to put human at the center of what we do. And it seems quite a bit funny to say that AI will basically work much better if we keep human involved and disrupt the traditional way of thinking and solving problem. So I would like to thank you all for that. And Jill, we can maybe switch to Q&A questions if you're okay.
Yeah, thank you both, Louis and Martin, for that excellent presentation there. We do have some questions that came in, so we'll try to get through a few of those. We've got a few minutes left here in our allotted time. I do want to remind you, though, feel free to type in your question and ask those. And then if we don't get to your questions today, we will reach out back to you again and follow up directly with you. So with that, I'm going to open up our Q&A session. One of the questions that we have here is, we have a conventional activated sludge plant that was not designed to handle BioP. So what are the typical conditions where your software can achieve BioP in such conditions?
I can try and respond to that. So if it wasn't designed for this, basically what we'd be looking for is what is the load fluctuation to your plant. So how much is the load changing over the course of a day in terms of nutrient concentrations? If during the night, for example, where flow theoretically should be at its lowest, you're way below your design capacity and your treatment capacity, then we can see that there's room created here to make the best of that time. So we'd be definitely looking at what is the treatment capacity now installed with regards to blowers and effluent requirement, and at the same time, what kind of loading is that plant receiving? And from there, we could do an estimate of how much time we could introduce anaerobic situations, and thus introduce BioP a bit more into your process day.
Great, thank you, Louis. Another question is, say we have a wastewater treatment plant of around, say, 45,000 PE, and we want to review the OPEX consumption, and more specifically with that coagulant and aeration costs. How do you make calculations about the potential ROI?
Louis, I can maybe take it from this one. Basically, what we do, we have with the history of Louis and his team, we've made some very detailed spreadsheets, including a lot of different variables to basically be able to assess the actual cost, and also to be able to assess the actual potential for optimization. So even though it's not always exact and fully accurate, it gives already a very good idea about the potential saving we can look at just running our spreadsheet and numbers. And after that, the next step is how if we do things differently, and that's maybe another step for optimization.
Great. Another one that we have here is, can you give us another example maybe of CAPEX avoidance?
Yes, for sure. Well, actually, there is another possibility if we look at the other side of the scale. So on this one, I tried to pick two, let's say, fairly typical clients here in Denmark. But moving a bit south to Poland, we were actually there from the beginning in the design and build of delivering a large plant to Warsaw in Poland. And here, the advantage of using AI from the very beginning of a design build project is that you can embed the thought into your project. So in that way, we are actually able to reduce by 15% the amount of concrete that needed to be built for the clarifiers. So the clarifiers were all designed with 4 meters in diameter less than what a conventional engineering design would dictate, because we knew that instead of building with a little bit of extra size for security, well, we'll instead build it with real-time control embedded, so that we don't need to build extra concrete, but just integrate a good level of data. So that, of course, meant a lot of savings in total. As we all know, concrete is not exactly cheap.
Great. I think we've got time for maybe one more question here. Question is, could we program the same algorithms into our PLC?
Well, maybe I can take this one. You know, as we said during the webinar, there is two aspects of it. First, you know, to train, you know, a PLC is composed by simple logic operators, A or B, plus, minus, and so on, and some I would say some simple mathematical formula. And if if you ask the PLC to say, can you do something different? Can you look elsewhere? Can you take much more data and try to start juggling with it? It's basically not what is done, what is built for. And even though PLC will become more powerful, I mean, if they don't include a smart operator on the side of it, it's not the typical task they can do. So I would say that it's not just a simple algorithm or a simple formula that we can program. It's really another way of looking at a specific problem. Louis, you want to add something on that?
No, maybe just very well. Just on top of my head, the last point, it's, well, of course, nothing is impossible for a great PLC programmer. I would say that you can go very far with your PLC. But thanks to the platform nature of Industry 4.0 and digital tools, you can benefit from what other people have already done. So instead of starting from scratch yourself and trying out algorithms on your PLC, by connecting to something like this, you're ultimately already connecting to something that's tested and that's tried and that's developed. So it's also a matter of how much do you want to spend trying to get to that advanced point? If it already exists somewhere, isn't it smarter to maybe just use that instead of trying it off yourself?
Yeah, and I think to add that, Louis, to if you look at other sectors, other like healthcare, aerospace, or banks or finance, they're already using cloud, and there is no way they would go back to PLCs and ladder logic, because we're not talking the same range. We're not talking the same kind of power. Basically, it's like talking about a US robotics modem in the 1990s at the end versus today iPhone and Android. We're not talking the same range, and they're not done for the same thing. And PLC are still here to stay. I mean, it's a great thing. It's very powerful, and I think the AI approach is just another tool that works in collaboration with PLCs.
Great. Well, thank you both, Martin and Louis, for that very informative presentation. And I'd like to thank everybody that was in attendance today as well for joining us. I do want to make a quick note. Over in your handouts panel, there is a download. Feel free to download that. That is the Wave magazine that is available to you specifically around digitalization. And you will receive a copy of that in a follow-up email as well. So with that, that concludes our webinar today. I do ask, though, if you would be so kind to take that brief survey that should show up on your screen as soon as the webinar concludes. We would greatly appreciate that. And feel free to check us out over on our website, veoliawatertech.com, to check out the upcoming Veolia Water Tech Talks as well. So with that, that concludes our webinar, and we do appreciate you joining us. Thank you very much.